This is the last lecture, and I will prove the main goal of the entire course of lectures, which is a theorem due to Hermann Weyl. We saw G is a compactly group connected Lie group, T a maximal torus, delta the set of roots of G and with respect to T. These are eigencharacters which occur in the adjoint representation, eigencharacters of T, and xt is the all characters on T. And we will also refer to them as weights. And one introduce an order a lexicographic order, as it is called. It's a total order on xt tensor R C. Xt is the character group. It's an abelian group, and we write it additively. Though when you regard them as functions on T, they are adding two characters amounts to multiplying the two functions. And we denote by delta plus the set of positive roots for this order, and pi the set of simple roots. Then one has an inner product, a positive definite inner product on xt tensor R Z, which I denoted this. And then a weight lambda in xt is dominant if 2 lambda alpha alpha is in non-negative integers for every alpha in pi. And the theorem I proved last time, or maybe the time before last, is the following: given any lambda dominant G compact connected, will also assume simply connected. We know that any compact semi-simple Lie group, for any compact connected semi-simple Lie group, the universal covering is automatically compact, and therefore this would be, if I say compact connected group, I want it to be also simply connected, then it automatically means it is semi-simple. Given any lambda dominant, there is a unique up to equivalence irreducible representation lambda of G, you need to reduce to finite dimensional representation. Rho lambda of G such that all the weights of rho lambda occurring as eigencharacters of T are of the form lambda minus sigma m alpha alpha, maybe I should write m lambda alpha alpha, alpha in delta, alpha in pi, m lambda alpha greater than or equal to 0. Moreover, every representation, every irreducible representation is equivalent to rho lambda for some lambda, for some dominant lambda. This is the theorem we have proved. Okay. Now, in this lecture, what I am going to do is to determine the character of any given rho lambda. So, what is, we know that the representation of a compact group is completely determined by its character, namely, so we know that if rho is a representation of G, a compact group, then rho is uniquely determined by the function G going to chi rho of G, which is, this is the definition of chi rho, trace f G, trace rho G. And so the rho is determined by the character. That is why we would like to know what the character is, whether we can write down the character given the representation. The representation, of course, is parameterized by the dominant weight. So, what is the corresponding character is what you have to find out now. That is what that is the theorem due to Hermann Weyl. I am going to state it presently. Rho is uniquely determined by the, maybe, yeah, I am sorry, this rho is going to be used for something else also. It is poor notation, but I think it can't be helped. Rho for a representation is a very standard thing, but it is also used for half the sum of the positive roots, unfortunately, but I don't think it will cause any confusion. Let me say, so notice that chi rho G satisfies, is a class function. That means chi rho G, chi rho H G H inverse, chi rho G. This implies chi rho is determined by its restriction to T. After all, every element in the group has a conjugate in T. So, chi rho is completely determined for a connected compact group. Chi rho is determined for know it in T. So, to know chi rho, it is enough to want to determine chi rho lambda restricted to T. If we know it restriction to T, we know it for all of G, because every element is conjugate in T, and that is the. Observe one thing, this chi rho lambda restricted to T is invariant under the Weyl group. Observe that chi rho lambda, first of all, being this trace, it's when you restrict to T, it's a sum of characters. Every eigen on every on every eigen value for T, eigen vector for T, it acts by multiplication by a character. So when you want the trace, you just have to add up all the characters occurring there. Some weights may occur with multiplicity, may not be of dimension 1. The highest weight, however, occurs exactly once. I mean, it's with multiplicity 1, because we know that we start with the highest weight, and the entire thing is entire vector space is generated by applying the enveloping algebra of n minus on the highest weight, which is why every weight is of this form.
The statement you have to say that lambda occurs also.
Sorry?
Highest weight lambda occurs is not mentioned in the statement, theorem statement. In the statement of the theorem,
Yeah.
lambda occurs is not there.
Lambda?
Lambda occurs as a weight is not there.
Yeah. Oh, yeah. But no, this already tells you that. It doesn't say that lambda is a weight. Okay, I agreed. Lambda is there's a unique irreducible representation rho lambda of G, such that all the statement is correct, though it doesn't tell you immediately that lambda has to be the highest weight. Okay. Yeah. Lambda is a weight. Okay. Also, where do I write it? Lambda is a weight of rho occurring with multiplicity 1. That should go here. I think now it's okay. Rho lambda. Yeah, okay. Thanks for pointing out. Okay. Yeah. Chi rho lambda restricted to T is invariant in the Weyl group, because Weyl group elements, how do they operate? They are coming from the normalizer of T. Among the inner conjugations, there is also inner conjugation by elements of normalizer of T, and therefore the function has to be invariant under the when you have something which is a class function, it has to be, when you restrict it to torus, it has to be invariant under the Weyl group. Okay, the Weyl group W. Okay. Now, yeah. Now we have seen. I don't know if I proved this statement. If I have not proved this statement, let me know. So I will prove it now. If let AT be the set of elements in ZT, this is the group algebra of XT, and therefore is an algebra of functions on an algebra of functions on T. Be the set, the subspace F in ZT sigma F equals epsilon sigma f for every sigma to Weyl group, where epsilon sigma is signature of sigma. This is AT, and we have also ST equals F in ZT sigma F equals F sigma n W. Then I stated this theorem. I do not know if I proved it. The point is, theorem says that ST equals AT into delta, where delta is sigma in W epsilon sigma rho, where, my apologies for the notation, where rho equals half the sum of the positive roots sigma alpha and delta plus. It's equivalently rho is the dominant weight satisfying 2 rho alpha by alpha alpha equal to 1 for every alpha in pi. That is rho for. So, the point was AT itself can be described as the AT CF, the vector space C of this is C span of A lambda dominant, and A lambda being equal to sigma epsilon sigma lambda sigma lambda. For every weight you can do this, in particular for dominant weights. Notice that this sum, when you take anything in the orbit of the dominant weight, which says, now take a mu which is in the orbit of the dominant weight under the Weyl group, then there lambda equal to a mu opposite sign, depending on the element of the Weyl group which takes lambda to mu. So, this, when you take any element of ZT and do this averaging process sigma, you can do this averaging process sigma epsilon sigma lambda, sigma f for any f in ZT. Then you land in a function which will be alternating with respect to the Weyl group. And since every element of ZT can be written as linear combination of characters, you find that every alternating function can be written as a linear combination of A lambda, as lambda varies over dominant weights. So, let me make that statement. Let me put it like this, okay. Proposition, the A lambda lambda dominant are, let me write A lambda plus rho lambda dominant are linearly independent and span AT. Every alternating function which is the linear combination of characters on the torus is necessarily the form is a linear combination of the A lambda plus rho with lambda dominant. If every element which is alternating with respect to the Weyl group is necessarily an average like this. If you start with something which is alternating, and you average that, you get it back. Because of that, you find this mapping which takes lambda to epsilon sigma f to epsilon sigma f is a projection, is a W invariant projection of what I call ZT on AT. So, in particular AT in ZT is injective, and this is so every element of this is got from this by this. Now, every element in AT is necessarily the form A lambda plus rho as lambda varies over dominant weights. The point is, you could have taken A lambda which is not of the form lambda plus rho, but then which is dominant. However, if lambda alpha is 0 for some one alpha, then the alternating sum becomes 0. Note that if lambda alpha by alpha alpha is 0, then A lambda is 0, because if you apply S alpha, you find S alpha of lambda will be lambda itself. So, in the sum you can write epsilon, you can take the coset classes modulo the group generated by S alpha, which is a group of order 2, and in each of them you get terms with opposite signs which will cancel out. Okay.
Summation you have to divide by cardinality of W also.
Well,
For the projection,
to get a projection, you are right.
summation.
Yeah, sure. It's not when I say
Summation.
well, summation, yes, because sigma and W, and then 1 over order W, if I want a W invariant projection. So, otherwise it won't be a projection, it will be a map which will scale things up a little bit, scale things up by order of W. Okay, so because of that, when I do that is why I need only take lambda plus rho. If lambda alpha is 0, even for one alpha, then the A lambda plus rho which you get will be 0. And if it's if lambda alpha by alpha alpha is not 0 for any alpha, then it can be written as mu plus rho, where mu will be dominant. If you start with a mu which is dominant and such that 2 mu alpha by alpha alpha is greater than 0 for every alpha, then you can look at mu minus rho, that will again be dominant, and so mu can be written as mu minus rho plus rho. Mu minus rho will be lambda. So, okay, that is one proposition, and this second proposition which I wanted, which I essentially proved it last time, but this proposition I probably haven't proved, but it goes like this. Let the map lambda going to the map f going to f times delta. I have this element delta here. So, I have already stated it as the theorem. Okay. This theorem tells you that AT is spanned by this, and I want to say ST equal to AT into delta. Okay. So, how do you get elements of ST? Proof of theorem. Elements of ST are or if you like ST itself, let me write ST is the span of I have not introduced that yet, S lambda dominant, where S lambda equals sigma 1 over W, if you like, sigma sigma lambda sigma in W. These are symmetric elements under the Weyl group. So, the summation of, if you take any lambda and sum it up, you are going to get this. And any function I am interested in is a linear combination of lambda. Notice that if take any lambda in its W orbit, there will be a dominant lambda, and when the so if mu is W of lambda implies S mu equal to S lambda to or equal. So, you need only bother about dominant ones, because in every orbit there is a dominant weight. So, S lambda is this, and so it is enough to prove that S and the S lambda is a span of this. So, it is enough to prove for every lambda dominant suffices to show that S lambda is in AT delta for every lambda in every lambda dominant. That is what you have to prove. Now, this is proved by induction. Using the order on xt. So, what happens is, so fix a, suppose you write the characters, the dominant characters are lambda 1, lambda 2, q in n in increasing order. Increasing in the lexicographic order. Lambda 1 is necessarily 0. I am looking at dominant characters, so lambda 1 is necessarily 0. And then if you look at AT into delta is, oh yeah, lambda 1 equals 0, then yeah, I am sorry, ST is I am not, yeah, okay. So, what you have to prove is that you necessarily have, we have to prove that when lambda 1 is 0, the character is a trivial character, constant function 1, we have to prove its I think, yeah, 1 by delta doesn't, sorry, what am I saying here? AT divided by delta, it is not a multiple. So, when you have lambda 1 equals 0, it is clear that 1 equals in AT, yeah, you look at a row which is delta by delta. When lambda 1 equals 0, 1 equals, so lambda 1 equals 0 means the character is trivial character. this is the additive notation. So, in the multiplicative notation it becomes 1 equals a rho by delta. So, you can start the induction. Okay. Suppose you proved it, assume theorem proved for yeah. So, the right way to say is delta times st is at. This is what one has to prove. I mean, what it means is that any alternating function is divisible by delta, and the quotient is precisely a symmetric function. Notice that z of t is isomorphic to the polynomial ring C T1 inverse, T2 inverse, etc. TL inverse, where L is the rank. It's the T is the polynomial ring can be identified with, I mean this ring ZT can be identified with the polynomial ring with inversions of this kind, T1, T2, Tn with all the Ti inverted. Okay. So, assume that this has been proved for up to for lambda I less than or equal to r. Let us look, then we are interested in lambda r plus 1. So, we have to prove that delta times symmetric lambda r plus 1 sorry, and what am I doing here? Just a moment. No, what I will do is the following. Sorry, let us look at a of lambda r plus 1. Okay. This is the alternating sum epsilon sigma lambda r plus 1. Sigma and w. Okay. All right. Maybe I'm missing a 1 over w. Yeah, if I wanted the projection and so on, I may need 1 over w, but I 1 over w. Let's a lambda r plus 1 is this. But this equals, notice that the sum of so a lambda r plus 1, maybe I should, yeah, I've set it like this, delta st equal to at. I need to prove this. So, what I have to prove is, yeah, I'm sorry, this is what I have to prove. Okay. Now, look at the elements of at, they are all of the form a lambda plus rho, where lambda is dominant. So, you now have this. So, when a lambda 1 plus rho, when lambda 1 is 0, this is a rho, which we know is delta. This is delta times 1. 1 is symmetric. So, you find that you can start the induction. So, I am proving the increasing order. So, proof by induction. Now, look at, suppose I have done it up to that. Now, look at lambda n plus. So, assume a lambda q plus rho is a linear combination of delta times S of lambda I 1 less than equal to I less than equal to, sorry, lambda, yeah, 1 less than equal to I less than equal to q. suppose I proved it for lambda q up to lambda q, that all the, assume that a lambda q plus rho is, let me write lambda j plus rho for 1 less than equal to j less than equal to q, delta s lambda I 1 less than equal to I to q. Suppose I proved that a lambda j plus rho is less than equal to this for all 1 less than equal to j less than equal to q, I want to prove it for q plus 1 then, that is induction. So what happens for q plus 1? So I look at a lambda q plus 1 plus rho. Now this is a linear combination notice that lambda q plus rho is dominant. So when I take anything in the Weyl group orbit, it will be of the form lambda q plus 1 plus rho minus some sigma m alpha alpha, where m alpha are all non-negative and alpha simple roots. So this is a linear combination of elements of the form lambda q plus 1 plus rho minus sigma m alpha 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 and pi. Anything in that is of the form. Now look at the right side. Now I'm lambda q plus 1 plus rho is of this form. So when I the alternating sum consists, so you will have a lambda q plus rho plus 1 plus rho is of the form some coefficients c whatever, yeah, c of I'm taking the alternating sum of this, and then which is I'm going to apply the, when I apply the Weyl group element, it's going to be of this form. No, wait a moment, what am I saying? Yeah, anyway, so linear combination of elements of this form. Let me keep it as it is. Now I want to say it is, now look at the element delta times the symmetrizer of lambda q plus 1. Yes, lambda q plus 1. Symmetrize this, look at this product. This also involves a linear combination of lambda I plus lambda I plus lambda I minus sigma m I alpha 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 and pi 1 less than pi less than equal to q plus 1. Because what happens in lambda I plus rho minus this kind. It's a linear combination of elements of the form. Because see here you start off with rho and various Weyl group transforms, and here you are using lambda q plus 1 and various Weyl group transforms. So when you do that, you may get some, I'm going to add up things, you may get some dominant weights, but whatever dominant weights you get, they will be of this form, okay, and they are Weyl group elements. So they are all of the form, it's a linear combination of lambda I plus rho minus sigma m I alpha alpha, and therefore and we know that this is alternating, so it is going to be the alternation of lambda, it is going to be a combination, a linear combination of a lambda I of a dominant weight of the form lambda I plus rho minus sigma mi phi. Which means implies that delta S lambda q plus 1 is AF is linear combination of A lambda I plus rho, as rho varies as I becomes less than or equal to q plus 1. But those with I less than or equal to q are already in the space we have described already. The induction hypothesis tells you that all this belongs to this, implies delta S lambda q plus 1 equals A lambda q plus 1 plus rho with some coefficient C times this plus linear combination of delta times S lambda I with I is equal to q.
One of the important fact is that all these combinations, this will be W invariant also. That's why this.
Yeah. I mean, it's
The weights occurring here.
no. By induction hypothesis, the what I have done, assume that Aj lambda plus rho is a linear combination of the earlier ones, which is all the A lambda I plus rho are linear combinations except the q plus 1 corresponding to q plus 1. That is how you get this by induction hypothesis of this. This is by induction hypothesis.
Also the W invariant plays a role. This setup makes it W invariant. That also plays.
Which is the sorry?
Delta dot S
Yeah.
lambda q plus 1 is a linear combination of these weights.
Yeah.
And also this set is W invariant. That's why you
W invariant, yeah, sure. I mean, no, when I multiply something which is invariant by this delta, you get a W not invariant, which transforms according to epsilon sigma.
WI.
Yeah. W alternating, that's the kind of thing we get. Okay, so that proves the theorem. Now, we are now ready for the Weyl character formula. So, theorem, Weyl character formula. So, it is the following. If rho lambda is the representation corresponding to the dominant weight, lambda, chi of rho lambda on any t equals, t is in the maximal torus, A rho plus lambda divided by A rho. A rho plus lambda is alternating and so is A rho, so the ratio is symmetric. Okay. And we know that A rho plus lambda is divisible by A rho. So, what you get is the good function on the torus. Okay. I mean anyway, so this is a good function on the torus, and So, for instance, I mean a rho can be 0 at some place, but at the same place a rho plus lambda also is 0. So, the ratio will make sense. I mean that is the content of the theorem that delta S T is a key. Chi rho lambda T is a symmetric function on the torus. It is a character. So, class it is invariant inner conjugation, therefore, W invariant. And what this says is that this alternating function is always some multiple of a rho by some symmetric function. This symmetric function turns out to be the character for this particular a rho plus lambda. That is the theorem, Hermann-Weyl theorem. How do I prove this? Once again, we will do the same thing as we did here. We will argue by induction. Induction on so proof is by, once again, let lambda 1, lambda 2, lambda 3 be the dominant characters weights in the lexicographic order. Then we want to say that we will prove by induction that chi lambda r equals a of rho plus lambda r divided by a rho. The point is this: we know that chi lambda r chi lambda s bar dt dg over the compact group G is 0 if r not equal to s and equal to 1 if which way is it? Sorry, equal to we normalize the Haar measure. This is dg is Haar measure, and we assume that integral dg over g is 1. So, when you have this is equal to n if is it n or it's 1, yeah, 1 if r equal to s. We have these relations among the characters, because characters are they represent the inequivalent if r is not equal to s. So, we have this relationship. Now, the point is that you are integrating a class function on G, but what you can do is the following: you look at the mapping G cross T to G. We know it is a surjective map, and this factors through this map is nothing but G comma T going to GT G inverse conjugate. This factors through G mod T cross T to G. Now, if I take we have the Haar measure here, which is dg. The pullback of this measure under this map is a measure on G mod T cross T. That's what you are going to get. Okay. What is that measure? It turns out it is d of G mod T. There is a unique invariant measure on G mod T, because G is compact. You take some measure on G mod T and average it over G, you will get an invariant measure there, cross the measure on T, the Haar measure on T. Turns out this times delta function delta, which we defined. It is a function only on T, delta bar. This is the pullback. So, this mapping, let me call it phi star of dg equals this, where we have taken the R measure on t to be 1, on g mod t to be also 1. So, this is normalized measure with measure of g mod t cross t equal to, I have to be careful here, anyway, write 1. It may be mod w, I am somewhat uncertain. See, the point is that when you pull back, this is a outside a set of measure 0. If you omit a set of measure 0 here, it turns out to be a covering, and covering by Weyl group, the group is the Weyl group. So, when you pull back the measure here, so it should be you want the pullback has total measure 1 here. So, if you take, but when I say pull back, no, the measure will be this, sorry. So, it will be normalized with measure this equal to mod w. This is, if you omit the singular set in T, that is those which are in the kernel of the various characters alpha, if you omit that, what you get is an open set here, and that the covers the image, it is a covering space of the image set. Image set is a set of complementary set of measure 0, so it will have measure 1. So, when I pull back with the measure, I am going to get the, since the fiber is of the cardinality of w, I am going to get g mod t cross t equal to w. So, that is the measure which you get. So, what we want is to integrate. Let us see what happens to the integral here when I pull back. Chi t, chi lambda r, chi lambda s bar dg on the group G, which is equal to delta rs with normalized measure. When I pull back, I can pull back the function and integrate it here. I am going to get chi lambda r delta, this is, oh, I know this is equal to Ts, okay, but this means when I pull back to the toes here, you get a function which is independent of g mod t, independent of the variable in g mod t. So, if I write chi lambda r composed with phi times chi lambda s composed with phi, and here I am going to get, this is the pullback, and dg pullback is phi star of dg, integral of this equals delta rs into mod w. Okay, but this is same thing as, we know that phi star dg is what, chi lambda r composed with phi, chi lambda s composed with phi, phi star dg is dt dg, I have written the delta bar dg dt dg g mod t dt is what I have. Okay, and this is equal to delta rs. I am rewriting this, pulling back, and I have a w there, the total measure of G mod T by T is W, so that is why this W get cancelled out and you get this answer. Okay. Now, what I am going to, by induction hypothesis, I know chi lambda r equals A lambda plus R, A rho lambda plus R by A rho, and if I look at chi, I am now looking at chi up, so assume chi lambda r equals AF rho plus lambda r by A rho for r less than or equal to q. Then if I look at chi lambda q plus 1, it will be, it's a sum of weights with counted with multiplicity, sum of weights with multiplicity occurring in, I am interested in chi lambda. See, when I compose, I get a function on G mod T cross T, which is really invariant under G. So it is a function which is essentially a function on T, and the integration on G mod T therefore is irrelevant. It is the volume of G mod T is what you are going to get. So it is essentially integration over T. So what you got is these two are independent of the variable in G. So in G mod T. So the integration is only with respect to dt, with respect to the torus. So you are going to integrate this with respect to the torus delta bar chi r. I know that this is equal to, if these are characters, so this is equal to delta rs. Now on the other hand, look at the other expression which you have. A lambda r plus rho A f lambda r plus rho into A f lambda s plus rho I want to prove that chi lambda r is nothing but A lambda r plus rho times delta. So once again, if you look at these expressions, if you see, the point is, if A lambda A mu, if you look at lambda mu dominant, this integration, sorry, what? Oh, so yeah, sorry, I'm dividing this by delta bar. So this expression is just this A lambda rho plus r into A lambda rho, A lambda s plus rho. That's the product which you get. This whole thing is just this. I mean, I'm comparing. I have to say that this is equal to this. This is equal to this. I'm comparing the two. So I write this down. I get A lambda r plus rho and A lambda s plus rho. This dt is what I'm going to get. But this integral equals again delta rs. Why? Because if you look at this integral, this I'm averaging lambda r and lambda s. If lambda s are distinct dominant weights, their Weyl group orbits are distinct. So no two elements in the Weyl group orbit, no element in the Weyl group orbit if this is equal to the Weyl group element in this, and therefore the product integration is 0. Two characters which are distinct, chi bar, chi 1, chi 2 bar, dt is 0. So you find that when r not equal to s, all this is 0. It is true for the characters, it is true for this also, and both of them only involve the, so the expression for A lambda r plus rho, A lambda s plus rho, if you and chi lambda r composed with V times delta. If I look at this, A lambda r plus rho and chi lambda R composed with phi times delta. Look at these two. Notice that it is, this will involve only the various Weyl group elements, Weyl group transforms of lambda r plus rho, while this a priori may involve something Weyl group transforms of various weights of this character, various weights of this representation. But the various weights of this representation lambda r times, I mean weights of this representation times the weight of this representation, but they are all less than or equal to lambda r plus rho. They come in the, therefore they are already involved in the previous characters. Okay, so the point is chi lambda r, let me write chi lambda q plus 1, times delta. It's a very similar argument to what we did a little earlier. Involves alternatization of elements of the form lambda r plus rho with r less than or equal to q plus 1. But all this by the induction hypothesis all this alternating sums are linear combinations of characters, no sorry, linear combinations of dominant weights of the form lambda r plus q by induction hypothesis. Sorry, what I want to say is this: by induction hypothesis, all the alternating sums of lambda r plus rho with r less than or equal to q are to be found are linear combinations of chi rho s times delta with s less than or equal to q. So, the only new character is the only new thing which occurs. So, the only new term is a of lambda q plus 1 times delta. Rest of them are already subsumed, and the orthogonality relation tells you it comes the character is the linear combination of what it says is the linear combination of this plus character times delta is the linear combination of this with along with a lambda I less than equal to q. But the a lambda I less than equal to q are already known to be in the image of the characters, and the orthogonality relation tells you that this has to be the new one has to be the. So, this implies a lambda q plus 1, sorry, the only new term is, I am not saying it right, the only new term is chi rho, yeah, sorry, chi lambda q plus 1 times delta. The only new term is this, and from that and the orthogonality relation follows that chi lambda q plus 1 times delta equals a lambda q plus 1 plus rho. Well, I am not explaining this very well, but it's an induction argument which is quite simple.
But cannot you observe that these characters that you have defined alternating sum
No,
data, they are also norm.
You see,
they have norm 1.
Sorry?
These characters that you had a upon delta.
Yeah.
They have norm 1 by the Weyl integration formula.
Right.
And once they have norm 1 by sure orthogonality, they must be irreducible.
They must be
Irreducible.
irreducible.
Yeah, because it's a character of norm 1.
No. Yeah. So.
So one would like to observe that because in sure orthogonality, if they were
No. I'm using the fact that the orthogonal relations. See, the point is that you start with you have a bunch of these characters which are orthogonal, which are mutually orthogonal up to r less than equal to q, and you have these other expressions which is these are orthogonal, and therefore it also follows that this chi lambda times delta are orthogonal, and this is a bunch of orthogonal thing, and you have on the other hand you have the alternating sum a lambda r plus rho. These are also mutually orthogonal, these are also mutually orthogonal, and you notice that this is a linear combination of ones because of the induction. We up to this, everything is a linear combination of the corresponding things, and when you take the next one chi lambda q plus 1, when I write it down, this times delta I have to prove is a lambda q plus 1 plus rho. We know that this chi lambda q plus 1 is orthogonal to all the earlier things, and our calculation shows that chi lambda delta by, so that would amount to saying chi lambda q plus 1, the same thing. If you look at a lambda r plus q divided by delta, that also has the same orthogonal relations, and they involve the same combinations of earlier combinations are the same for both, and so the only new term is a lambda r plus rho by a lambda r plus rho is the only new term, and so that has to be equal to a lambda r plus 1 by delta has to be equal to chi lambda r plus 1. That's the proof. Okay. Well, think over it. It's not difficult. It's I'm getting a little I'm not writing it out properly, so not getting it right. Anyway, so that is the Weyl character formula. So we know the dominant a dominant weight gives you a representation, irreducible representation, and we know its character now. That's the formula. From the character, of course, you can deduce the dimension of the group, dimension of the representation. This is again theorem, Weyl's dimension formula says the following.
I mean, one might say that you have used what is called the Weyl integration formula, which is also one of the important theorems.
Yeah, this is
The Weyl integration formula, and also
this I have not proved, but I will leave it as an exercise to check that out.
But no, it's called Weyl integration formula, and it is also one of the important results in the subject.
Yeah. I mean, so I should. This is the, well, maybe I state it as a theorem.
A lot of independent interest.
D g by t cross dt is by the equal times delta bar is phi star dg. Okay, that's a statement. There is a where dg by t cross dt is the G invariant, where dg by t is the G invariant measure on G by t, and dt is the R measure on T, chosen such that the volume of G by T cross T equals the order of W. This is the one which facilitates easy integration of class functions. Instead of functions on G, you get to functions on G by T cross T, and once the class function, it actually turns out to be a function is independent of the first variable. It's only a function on T, and so you're reducing integration on G to integration on T for class functions, not for everything, for class functions. Okay, the Weyl dimension formula says the following: dimension of rho lambda equals phi alpha and delta plus lambda alpha where is it? That is the dimension of rho lambda is given by this formula. Lambda, sorry, lambda plus. You see, each alpha determines a singular torus, okay, the kernel of alpha, and you can. The point is, if you know the character, you know the dimension by evaluating it on the identity element. Chi rho of the identity element is obviously the dimension of the thing. So you have the dimension form, the character formula is written down. It is so what you want is a rho plus lambda r, rho plus lambda by a rho evaluated at 1 at the identity element. But if you look at the numerator and denominator, they are both 0 at 1. As you can see. So how do I go about evaluating? You apply L'Hopital's formula. That is, you differentiate along some directions. You successfully differentiate along the directions H alpha. In the torus T alpha, one dimensional torus. I mean, if there are well, for each T alpha, for each alpha, there is also a one dimensional thing coming up by dualizing. The thing is that how do I say it? You have this element I H alpha. You have this element H alpha in the we had this basis for the every 3-dimensional thing. You have H alpha, E minus alpha, but that is the real thing. That is the I times that. So to get back into the torus, you get this element IH alpha. What you have to do is to differentiate along this IH alpha, both numerator and denominator. If you do it once, still the functions will be 0 at some places. I mean, this function. You differentiate with respect to 1 alpha, it's not enough. You will have to differentiate with respect to every positive root, alpha and delta plus. You will have to differentiate with respect to every positive root. Every time you do it with respect to positive root, you are going to get lambda plus root alpha as the derivative. So you do it for all the deltas, so you get this. That's how you get this formula. Each time you multiply, you will get 1 lambda plus rho alpha will pull out, and you will get a product of other things. Keep on differentiating, and that's the result. That's how you get the dimensional formula. Okay, I think I'm going to stop here. That's the conclusion. And I'm sorry this last lecture perhaps has not been as clear as some of the earlier lectures, but work it out the rest. I think it's worthwhile leaving something for you to think about and do it. I mean, that's not the reason for my doing it, but anyway, the result of the way I've given this last lecture. Thank you.